Good morning, class. This is Mr. Barris. So today we are going to do a review game in class on Module E, Unit 4, which is the Restless Earth. But as promised, and just like I usually do, I wanted to give you some review slides in a video format that you can watch before you take your test tomorrow. So this is probably the most difficult or the most extensive unit we've been over this year because it's got a lot of information. So I tried my best to include everything pre-written on the slides so that I can just go over them and so I won't forget anything. So first we're going to start with the composition of the Earth. Now the composition of the Earth, there's two ways that scientists have divided it over the past couple hundred years. We have divided it as concerning its chemical composition and concerning its physical properties, and you can see the division I've made on this page. With respect to chemical composition of the Earth, there are only three main parts, and you've known these since you were in elementary school. The crust, the mantle, and the core. Now, to be quite honest, I don't think any test I give you would focus on the chemicals inside these parts, so I tried to put the important things to know about these things underneath the different layers. So for example, the crust, there are two types of crust. There's oceanic crust and continental crust. Whenever you think of continents, that's continental crust because it's land. Oceanic crust is the stuff found deep on the ocean floor. Now generally, oceanic crust is thinner than continental crust, and we can see evidence of that because a lot of seismic and volcanic activity goes on underneath the oceans that we don't really even know about. So just think oceanic crust, very active. It's got to be a thinner crust than the land that we stand on. Inside the mantle, which is the largest chemical layer of the Earth, we see these cycles that I've drawn in there, and those are called convection cycles. So if you remember way back in the beginning of the year when we first started talking about convection is the movement of matter based on temperature and density changes. And so I've tried to model that here. Whenever you see this cycle going deeper into the Earth, that represents colder rock sinking. And whenever that arrow starts coming back up towards the surface, that's when warm rock starts rising because it's expanding and becoming less dense. And we're going to talk a lot more about that when we get into plate tectonics. Then finally we have the core of the Earth, which is the center, and it's got different characteristics that we're going to talk about when we get to the physical properties of these layers. But those three things are really the important key points for the chemical composition of the Earth. Remember, three layers and the different crusts, what happens in the mantle, and I think you're going to be okay. With physical properties of the Earth, there are a lot more divisions. So first things first, we have what's called the lithosphere, which is the outermost physical layer of the Earth. Now the lithosphere, I've tried to make it so that it's a little bit thicker than the crust on the chemical side, because the lithosphere is made up of the crust as well as a little part of the mantle. Okay. You can see I've put little cracks in it all the way around. Those kind of represent plate boundaries. So the lithosphere is where we see our tectonic plates. Okay, that's important to know. Right beneath that, we have what's called the asthenosphere. Now, the asthenosphere is it's a softer type of mantle that the tectonic plates kind of float on. Okay, so if you can remember, lithosphere is the plates, asthenosphere is what the plates float on. You'll be able to remember the order. Right below the asthenosphere, we have the mesosphere, not to be confused with the atmospheric mesosphere we already talked about this year. But the mesosphere is an even more soft type of mantle. You can see as we go deeper into the Earth, we're going to start getting more soft and liquid-like. After that, we have the outer core, which I've written in parentheses the cursive L to tell you that the outer core is a liquid, and the inner core, which I've denoted that is a solid. Okay. So you'll notice that everything on the right is really dealing with physical properties. We've been talking about things floating on each other. We've been talking about the density and the softness of the rocks changing. We've been talking about their states of matter, solids or liquids. Whereas on the left side of the screen, we could have dived into chemicals like oh, the core is made up of nickel and iron, but we didn't choose to do that because I don't really think you're going to need to know that on the test. So hopefully this is a good overview for the composition of the Earth. Let's move on. Okay. Next thing I want to talk about is the theory of continental drift. Now, the big guy who came up with this was a guy by the name of Alfred Wegener, and he did this in the late 1800s. Now here's an illustration from your book. I mean, you guys already know that the continents seem to fit together like a puzzle. What you might not have known is the names of the different sections of continents. So for example, the big landmass that existed 245 million years ago was called Pangaea. Okay. Now, 45 million years later, we started to see a north-south sectioning off of continent pieces, the northernmost part of which was called Laurasia, and the southernmost part was called Gondwana. You can clearly see what makes up each of those land masses. And then about 135 million years after that, we start to see the continents starting to assume the shape that we have come to know on our globe. And then 65 million years after that, we have where we are today, which, if you can imagine the Earth as it looks today, you can see this natural drifting apart that is called continental drift. That's pretty much all I want you to know about continental drift. So let's get on to some of the more fun stuff. Okay, so we're going to talk about some of the mechanisms that lead to continental drift. The most important of which, arguably, is called seafloor spreading. And there's a lot of information on this slide, so I'm going to see if I can help you out by highlighting certain things or circling things when I'm putting emphasis on them. But basically, in seafloor spreading, you've got this diagram here, which shows red arrows coming up out of the ground away from each other. That's supposed to represent warm rock expanding, becoming less dense than the rock around it, and rising to the surface of the ocean floor. Now, as warm stuff becomes exposed to the ocean and the rock above it, it starts to cool down. And you can see I've tried to mark that with blue arrows. So we have this red arrow that's meaning rock is rising, and the blue arrow means that rock is starting to cool down and fall back into the earth. Now, if you imagine this happening in a continual process, we can imagine, sort of like this. If you watch my fingers on the screen, this effect right here, where we have this spreading of the sea floor. Okay. Now, this puzzled scientists for a long time, because if we're always spreading out our continents and our sea floor, our Earth would be expanding its surface area, and we all know that really can't work because the law of conservation of mass states that we can't change an object's mass. We can't just keep putting stuff into the Earth to make it accommodate that surface area change. So if we're always expanding and spreading out the seafloor, it's also got to be going somewhere to recycle itself. And you can see I've circled in green some blue arrows that are going back down into the earth, because we all know that what comes up must eventually go down in the earth. So once again, we have seafloor spreading with the warm rock coming up above the cold rock, pushing it out of the way, and then the cold rock sinks back down into the earth when it becomes more dense than rock around it. Okay. It's a really cool mechanism, and it's kind of interesting thinking about how we discovered this, or without many tools at the time. But I want to go over some vocabulary words real fast. You'll notice in red I've written, when warm rock pushes on cooler rock, this is called a ridge push. Okay, so if you imagine this warm rock coming up and then pushing cold rock out of the way, it's called ridge push because you're making a ridge right here. Okay, if you can see my cursor, we're creating a mid-ocean ridge on both sides of this chasm. And B, you're pushing on the colder rock, and you're pushing it out of the way. You see my cursor? So that's why it's called ridge push, because you're making a ridge and you're pushing rock out of the way. Okay? Next, in green, I've written, when cooler rock sinks down into the earth, it pulls the connected rock down with it, which is called slab pull. Okay? So rock is all connected along here. So notice my cursor again. It's all connected right here. So if ridge push is pushing colder rock out of the way, and this colder rock is continually cooling and becoming more dense than the rock around it, it's going to want to sink back down into the earth, and it's going to pull the rest of this slab with it. That's why it's called slab pull, because this section of rock down here, which is sinking, is pulling the rest of the slab with it, since it's all connected. Okay? Sweet. Let's keep going. Now, when we get sinking rock going back down into the earth, you can see another chasm right here that we're forming. This is how we get deep ocean trenches. So if you imagine some of the trenches that you know of, maybe the Mariana Trench, a lot of those trenches form because of slab pull. But keep in mind, this whole process happens because of convection, and I'm underlining this right now. Convection. Convection in the mantle causes warm rock in the crust to rise above cooler, denser rock, forming a mid-ocean ridge. Sinking rock forms deep ocean trenches. That's basically how seafloor spreading works, and that's the premise of continental drift. Okay? Let's keep going. Continental drift was one theory proposed by one guy. Now, plate tectonics should not really be confused with continental drift, because continental drift is just explaining, the drifting of the continents apart to their current configuration. But plate tectonics kind of takes a more general spin on moving sections of the Earth. So they are different theories, but plate tectonics kind of expands on the theory of continental drift a little bit. Okay. So remember our lithosphere, how we sectioned it off into plates and how they float on the asthenosphere? We're going to talk about each of those plates right now. Okay. Now plates, you can look up a map of the Earth and the different plates. There's several involved. Most of them are probably found in the Pacific Ocean, where a lot of our seismic activity happens. But let's just zoom in to the boundaries between different plates on the Earth. Okay, we have three different types of boundaries. We have a convergent boundary, a divergent boundary, and a transform boundary. Okay, I've tried to draw arrows to show what's going on in each of these boundaries. You'll see convergent boundaries always have arrows going towards each other, meaning that plates right next to each other are pushing up against each other. Okay. Now, when this happens, there's a couple possibilities of what's going to happen to the rock surrounding this boundary. When plates are pushing on each other, rock might start to buckle, okay, forming mountains. So imagine if you were to take this pencil, say, and push really, really hard, maybe even start to bend it a little bit, you can start to see the pencil starting to buckle. Okay, it's starting to bend. But this is a solid, so how can a solid bend like that? Well, it's made of wood, which is soft and can bend a little bit. Rock, believe it or not, is the same thing. Rock can bend to form hills and mountains. Okay? But that happens only when plates push against each other, causing this buckling effect. Let's see that. Okay. Another possibility, when plates are pushing up against each other, if one is cooler or more dense than the other, we could start to see a sinking effect, and one plate might just overlap another one like this. Okay? This sinking of this plate right here is called subduction. Okay? Now this could happen underneath the ocean, this could happen between the land and the ocean, this could even happen on land. But just keep in mind, there's basically two ways that converging plates can interact. Next, we have divergent boundaries, which is where plates move away from each other. And we already talked about this a little bit. You'll notice this illustration for divergent looks similar to our seafloor spreading diagram right here. So once again, I've tried to show you that as plates move away from each other, we have the cooler rock kind of being pushed out of the way, the warmer rock rising above it to make ridges. When those ridges move apart, we start to get rift valleys. So I feel like divergent, you should already know that by now. The third type of boundary is called a transform boundary. So if you think about all the different ways the plates can interact, they can push up against each other, they can move away from each other, they can also move side to side against each other like this. Okay? So in transform boundaries, we have this horizontal movement of plates against each other. Now, you can imagine if you were to take, say, a rock from outside and take another rock and rub them against each other, you might get some serious grinding. But that isn't quite what earthquakes come from. It's not the grinding that causes the ground to shake. It's really the slippage, which I've written here. And when I say slippage, imagine taking a rubber band and stretching it past, what it's normally stretched at, and then letting go. The rubber band's going to snap back in its place. So it's slipping back into place. You can imagine if rocks rub against each other and cause stress to the point where they're bending beyond what they normally are at, they want to snap back into place, which is called slippage. That's what earthquakes come from. We're going to talk about that in a couple slides, though. Okay. The next thing we talked about in class was deformation. Okay. When you think of deformation, it might sound like a tricky word, but inside the word deformation is the word deform. So if you say that something is deformed, that means it's kind of got a change in size or shape that's kind of distorted from what it usually should be. That's how you can remember what deformation is. It's the same thing with rocks. If you start putting pressure and stress on rocks, kind of like our pencil where we start to bend it, even though it's a solid object, we start to deform it, change its shape. Okay? And it's kind of counterintuitive because rock is solid, dense stuff. So how can it bend to become something else? Well, it happens. It's just a very long process. An example of deformation from stress is how rocks fold. Okay? So you can see I've kind of tried to color code different folding patterns in blue and red. But when you start to see a buckling upward of rock, like this, it's called an anticline. Okay? So just think anticline buckles upward. Okay? Then we have what's called a syncline where rock buckles downward. Kind of like this. The way you can remember that, syncline, you get this middle section kind of sinking down. That's a syncline. Okay? That's basically how rocks can fold. So yeah, that's an example of deformation. That's pretty much all you need to know for anticline and syncline. Just remember anticline upward, syncline rock buckles downward. Okay. Sweet. So now we're starting to get warmer and warmer towards discussing earthquakes and what really causes them. To do that, we need to understand kind of this slippage process, or how different sections of the earth interact with each other besides at boundaries. Okay. Now, if you were to take this pencil once again and bend it, if you bend it any further past a certain point, it's going to break. Okay. And actually, I don't know if you can hear it on the video, but I can hear this pencil starting to crack as I'm starting to bend it. And eventually, if I keep bending it very carefully without breaking it, you can start to see little cracks appearing in the pencil wood. Okay? The same thing happens when rock. Rock has a breaking point, and when it can't bend any further, you start to see cracks appearing in it. Okay? Those cracks are called fault lines. Now, fault lines are cracks in the rock that separates, these two different broken pieces, and these two broken pieces can now interact with each other in different ways. And I've put 3 of those ways down on this slide. Okay, so if you can imagine, there is 2 blocks or 2 plates separated by a fault line, and these plates are moving horizontally past each other. Well, that should look very familiar because we just talked about transform boundaries 2 slides ago. Okay, when you start to get these rocks moving past each other at a fault line, we call that shear stress. Okay, every one of these plate interactions or fault interactions is going to be due to some type of stress. This type of stress is kind of like shear. It's called shear stress. Okay, I'm trying to come up with an analogy. Imagine taking 2 magnets and trying to push them against each other. You might start to get some pushback due to the magnetic forces. That's kind of like shear stress. Okay. Interestingly enough, these strike-slip faults are the most popular causes of earthquakes. Okay, shear stress. That shouldn't say strike-sip. That should say strike-slip. So let me put an L in there. Slip. Okay. Next we have what are called reverse boundaries. Okay, or reverse faults. Excuse me. Now, in order to understand these next 2 fault interactions, we're going to go over some vocabulary real fast. So, first of all, if you have 2 fault blocks interacting with each other, one is more than likely going to be kind of hanging out above the other one. So I'm going to see if I can mark this in yellow. See how this block kind of hangs out above the other block? In geology, we call that a hanging wall because it's hanging above the lower block. And then we have this block down here, which is just hanging out. It's kind of always below the hanging wall. We call this the footwall. Okay. Now I've tried to draw arrows representing the different types of movement that's going to happen when these 2 fault blocks push up against each other. So first of all, you can see that these fault blocks are pushing up against each other. Okay. So this obviously then happens at convergent boundaries because we have this pushing up against each other. Now you can see, based on how the rock is wedged together, if you push these blocks together, you're going to get your hanging wall starting to move upward and your footwall is going to start to move downward. It all really just has to do with this incline between the 2 fault blocks where I'm putting my cursor right now. Okay, not really that difficult to picture. I mean, if you just took 2 wedges like a doorstop, if you took two doorstops and kind of pushed on their inclined planes against each other, you're going to get one naturally moving above the other. This occurs due to a type of stress called compression. And you can imagine if you're compressing something, you're pushing it together. That's going to help you remember convergent boundaries, which are called reverse faults. Okay, don't really know where the reverse comes from, but just see if you can remember that. Then we have normal faults, where once again we have our different walls. So here we have our hanging wall, and here we have our footwall. Now, normal faults occur at divergent boundaries, so you'll see the arrows pulling these fault blocks away from each other. Now, when you do this, the hanging wall is kind of just left hanging out there to dry, no pun intended. Now, when the footwall moves away from the hanging wall, you've got suddenly no support underneath the hanging wall, and that hanging wall is going to want to sink down. Okay. So what you're going to have pretty soon is a hanging wall that's far below where it used to be, and a footwall that's now higher relative to the hanging wall. The type of stress that causes these faults to pull away from each other at divergent boundaries is called tension. So if you imagine stretching a rubber band out, you're creating tension there. Okay. Okay, those are our different fault block types. Let's keep going. Okay. For a day or two, we talked about the different types of mountains that can form because of all these fault and boundary interactions. So this isn't really that detailed of a slide, but let's go over it anyway. So different ways that we can form mountains. When we push faults or boundaries up against each other, we start to see buckling of rock around it. Maybe an anticline appears or a syncline appears. And because of that, we can see the formation of, little mountains. Okay? So here we see some mountains formed by synclines and anticlines. Okay? Second type of mountain that we commonly form on the Earth is called a volcanic mountain. In other words, the Hawaiian Islands are a great example because those were once active volcanoes which spewed rock out of them, which hardened to form Hawaii. So that's pretty self-explanatory. Let's just keep going. Fault block mountains. Going back to this concept right here, where we have fault blocks interacting with each other, whenever they move towards or away from each other, one might be left hanging above the other one, or one might suddenly end up higher than the other one is because the other one collapsed suddenly. When you start to see blocks above each other, like a hanging wall, that is an example of a fault block mountain. And if you've ever been out to Wyoming, the Teton Mountains are an example of fault block mountains. Okay, nice, really easy. So speaking of volcanoes, let's talk about them a little bit more in detail. We've only got 6 more slides to go, so stay with me. Volcanoes aren't always just your typical, sloping mountain with a big hole in the middle. There are actually different kinds of volcanoes, and let's talk about them really fast. So volcanic mountains, there are 3 general types. One is called a shield, one's called a cinder cone, and then we have a composite volcano. So shield volcanoes, I've tried to draw one for you right next to the definition, but we basically have a gently sloping volcano. You notice it's not as steep as the drawings I've drawn below. And we also see, I've tried to put layers in here, layers of rock. The reason I put layers is because these volcanoes, they have gentle slopes that lava flows down over a wide area. So there's not really much room for, building huge steep slopes. It's just a gradual flowing out of lava down a gentle slope. And we start to get layers of lava on each other. And we have this nice sloping volcano. In contrast to that, the 2 below it, the cinder cone and the composite, you'll start to see, a more steep shape. Now, cinder cones, I think, are the most fascinating volcanoes because of how they form. Basically, what I've written here is that ash and molten material called cinders build up slowly around a vent, forming a cone. Okay, so it's kind of hard to draw that. So you see these zigzaggy lines I drew in the volcano? That's representing your cinders. So just imagine volcanoes are throwing up all these ash, all this rocks and dust, and that starts to build up around that central vent. And when this happens over and over and over again, over millions of years, those cinders start to build up naturally into a steep cone-shaped volcano called a cinder cone. And the last type, composite, you'll notice it's also pretty steep. And I've tried to draw layers and cinders just to show you that composites are kind of a mixture of shield and cinder cones. Not that they're gentle sloping at all, but basically we start to see layers of lava flowing out from a vent, but we also have cinders coming from the pyroclastic material that's exploding from the vent. Okay, feel good? Of course you do. I can't even hear you, so I'm just going to assume you're good. So next, volcanoes don't just have to be mountains. Okay, we can have cracks at faults that become volcanoes, and so you'll see here I've tried to draw a plate with a crack down the middle, and you can see lava wants to flow outward from this crack. Let me see if I can color code this a little bit. So here we have our lava flowing outward from the crack. Now the crack in this case is called a fissure. So when these cracks occur, lava wants to come up and flow outward, The resulting landform is a very flat plain of hardened rock. We call that a lava plateau. Pretty self-explanatory. Let's keep going. Next we have a crater. Kind of zooms in on a volcano. We're going to talk about just a certain section of a volcano called a crater. You'll start to see this little bowl-shaped depression that I've put on this volcano. And that's just telling you, okay, when lava erupts, we throw rock out of its way, causing this little depression called a crater. Now, I'm going to draw on top of this crater drawing just to kind of lead us up to the next landform. If you look at a volcano, you see a couple different things going on underneath it. You know, we have veins of lava, or magma, I should say, that kind of live inside a volcano. And you can see I'm drawing little vents on the sides of a volcano, but here I've drawn kind of a central cavity where magma can accumulate. Okay? And we call this a magma chamber. Now, if for any reason, let's say the magma drained out of one of these side vents, or maybe it just became cooler and drained out of this magma chamber for some reason, we would leave a big empty space right here. So let me see if I can show you that by erasing some of the stuff I just did. So if we drain this out and it's now empty, you've got a lot of pressure from the rock coming above it pushing down on this magma chamber. Now when that happens, we start to see the formation of a caldera. So you can see under caldera, I've drawn a bigger depression here to kind of show you that the magma chamber has collapsed. We have this big gaping hole right there called a caldera. Okay? Don't get the two mixed up. Craters are smaller depressions. Calderas are formed from collapsing craters. Cool. Let's keep going. All right, so here's some just general information to kind of finish up our volcano discussion. Most volcanoes occur at divergent boundaries, and you can imagine the fissure was a good example of that. Because when we diverge boundaries, when we pull plates apart from each other, we start to relieve stress on them and pressure on the magma below us, and it wants to come up. So that's how most volcanoes form. Composite volcanoes, however, which are the most violent, occur at convergent boundaries. So if you imagine plates pushing up against each other, let's say you've got a magma chamber underneath those two converging plates. When you start compressing things together, you start to build pressure underneath the surface of the earth, and that pressure wants to get relieved somehow. And so, the greater the pressure, the more explosive the eruption. So you can imagine that composite volcanoes at convergent boundaries are pretty dangerous. But also realize that volcanoes don't have to occur near boundaries. They can occur in the middle of a tectonic plate for all we know. Places where this occurs are called hotspots. Okay? Moving on. Okay, 4 more slides. So earthquakes. We've talked about volcanoes. We've talked about plates and faults. We've been kind of building momentum to start talking about earthquakes. Now, earthquakes have an anatomy, just like a volcano does. So you'll see I've drawn 2 fault blocks interacting with each other in this slide. The little star that I put down at the bottom of that little crack right there is called the focus of an earthquake. That's where the actual energy is released at a fault line. Okay, that's where the actual slippage occurs. And then I've drawn a dotted line going straight up from that focus to a point on the surface of the earth. That is called the epicenter. The epicenter is a point directly above the focus, and this is where the most shaking or damage occurs. Okay, so you can notice that earthquakes don't really even need to be felt at fault lines, which I always thought as a kid. Whenever you see the movies of an earthquake happening, you start to see this ground like splitting. But that's just Hollywood. That's not really what happens in earthquakes. Earthquakes happen deep beneath the surface of the earth, and the point where the most shaking is found isn't even towards the boundary at all. Where was I? Okay. we can see secondary effects of earthquakes happening all around us. In the ocean, when you have earthquakes going on underneath the water, and you can end up displacing a large amount of water and generating a humongous tidal wave called a tsunami. We already talked about those quite extensively earlier in the year, so we won't spend too much time on them right now. Let's talk about how we pick up signs that an earthquake has happened or is happening. Earthquakes release a lot of energy. Remember the rubber band example? When we stretch it beyond its capacity and it snaps back into place, that's energy. That's quite literally exactly how an earthquake works. Now, any release of energy is always accompanied by a wave. Okay, if you imagine the sun shining down on us, it's radiating solar energy. Well, solar energy is an electromagnetic wave. When you imagine the energy of heat, well, heat is seen in the infrared range on the electromagnetic scale, and so heat is also a type of wave. Okay, there's waves all around us. The same thing happens in earthquakes. When you get this snapping back of rock, when it's been bent beyond its breaking point, we see waves that start to appear. Okay, some of them we can actually see, some of them we can't. There are three types. The first two types fall in what are called body waves. So P waves are our first body wave. They travel fastest from an earthquake's epicenter, and they're picked up first by seismometers. Now I've tried to draw the motion of each of these waves below their descriptions. You'll see that P waves travel back and forth, back and forth, back and forth, kind of in a one-dimensional fashion. If you remember our Slinky lab, when we coiled up the Slinky and then just let it go, we started to see this back and forth motion. And you can see why they're fast. If it just needs to go back and forth, there's not really any reason for it to go really slow. The next type of body wave is called an S wave. These waves are a little bit slower, and they move from side to side along a horizontal line. Okay, because they move a little bit slower, they're going to travel at a lower rate than P waves, and they're going to be picked up maybe a split second, maybe a couple seconds, maybe even a couple minutes after P waves are picked up by a seismometer. The difference in time between P waves and S waves is called the lag time. And using math, we can calculate how far an earthquake is away when we know how much quicker the P wave arrived than the S wave. Okay, so those are our two body waves. We also have what are called surface waves, which are the slowest traveling waves. They're also kind of the most dangerous. So these waves move up and down. Okay, so I've tried to draw kind of a horizontal line representing the ground, and you can see the waves going up and down. And when we showed you some photos of bridges in class that kind of showed this really distorted shape, kind of like hills, those resulted from surface waves, so the most dangerous. Okay. Seismometers, I've already mentioned this word when we were talking about the different waves, but seismometers are basically machines that pick up these waves, and using data from different seismometers across the country or across the world, we can triangulate the position of an earthquake's epicenter. We did a whole lab on this. I hope you enjoyed that with the compasses and the map of the United States. But basically, if you calculate the distance away from a seismometer using the lag time, if you have 3 different stations, you can pinpoint exactly where that epicenter is. And that's called triangulation. Okay. Now, a seismogram is basically the picture that's made by a seismometer. And seismograms measure the magnitude of a quake according to a couple different scales. We talked about the Richter scale in class. It's kind of the bread and butter of plate tectonic earthquake stuff. So the Richter scale just measures the ground motion. Okay. For every 1 point the Richter scale goes up, the ground shakes 10 times as much. But more scientific is the moment magnitude scale, because that measures a lot of different things, such as the area that the earthquake's taking place on, the distance the fault blocks move, and how rigid the rock is. So that's kind of more scientific. We also measure earthquakes according to how intense they are. Okay. Now, it's kind of not really scientific to measure earthquakes' intensities because it's more a social impact that's measured. So intensity just measures how much damage occurs. Okay. So even if the earthquakes are the same on the magnitude scale, let's say in Africa or in the United States, if they're the same magnitude, it doesn't exactly mean that their intensity is going to be the same, because intensity measures damage. So if you've got a lot of great buildings in the United States that are designed to withstand earthquakes, and if you've got some buildings, let's say over in developing countries in Africa that aren't earthquake safe, even though the magnitudes might be the same, the intensities will be different because the damage will be greater in a place where you don't have as many earthquake-proof buildings. By the way, building materials are best in buildings when they are made of wood and steel. Concrete and brick is not a good idea because those things crumble and crack really easily. Wood and steel is a little bit more pliable. It bends, as we've seen with our pencil. So those are the most flexible and shake resistant and the best materials to make buildings out of. And guess what? We're done. So, hope you enjoyed this video. I hope it helps you as you study for the test. Good luck, and we will see you tomorrow.